Hi everyone, my name is Ryan Sinclair, and I'm going to present to you about radiation today from an environmental health perspective. We're going to talk about ionizing radiation and non-ionizing radiation. So the term radiation, again, it refers to energy traveling through space. Anything can radiate energy to something else. Some types of radiation are associated with radioactivity, and that's what we're going to focus on today. We're also going to talk about some types of radiation that includes neutrons that are uncharged, and also some non-ionizing radiation. So let's look at this electromagnetic spectrum. So non-ionizing radiation is everything to the left of the visible light, and to the right is the ionizing radiation. You can look at this in a variety of ways, but essentially everything to the right, starting with ultraviolet to X-ray and gamma rays, that's going to have some kind of medical effect on DNA. It's going to damage DNA. While on the left, infrared, microwave, radio, and some other non-thermal but extremely low frequencies, there's other types of health effects from those. And those are non-ionizing. So, for example, I have two things here. Here's a phone, and this is going to emit um, non-ionizing radiation. While this UV light here, this is going to emit ionizing radiation, ultraviolet light. So here's another type of diagram, and this one shows ultraviolet light, X-rays, gamma rays as more energy and ionizing radiation, while non-ionizing is visible light, um, infrared, microwave, radio and cell phone signals, and power lines. Here is an old picture from someone monitoring a building that might have some type of radiation in the paint or in the building material. There's a lot of types of stone that will have radiation in it. So ionizing radiation is anything that has enough energy to remove tightly bound electrons from atoms, thus creating ions. Usually we use this to generate electricity, kill cancer cells, and in many types of manufacturing. Um, this is a pretty typical image of the three types of particles coming out of ionizing radiation: alpha, beta, and gamma. Now, alpha particles are large, so they can't pass through human skin, even, or paper. Beta, on the other hand, can pass through human skin, but will be stopped by something, a soft metal like aluminum, and then gamma can go all the way through. There's anthropogenic sources of ionizing radiation and non-anthropogenic, so man-made or people-made sources of ionizing radiation: X-rays, consumer products, nuclear power generators, and then nuclear weapon-related things. And then there's natural sources: radiation from geologic formations, radio elements such as uranium, um, and you get radon gas as a decay product. Also, cosmic rays and other types that come from outer space. There's particulate energy and electromagnetic energy in the form of photons. Those are other types of ionizing radiation. So radioactivity, in short, is any kind of emission of energy that radiates out of a nucleus of an unstable atom. So in thinking about how radiation can interact with you in terms of an environmental health perspective, there's three types of measurements. So you're looking at on the far left is a tree with some apples that are falling out. So this is equivalent to, say, a number of disintegrations per second, or a number of becquerel. So you can look at a particular radioactive element and describe how these types of activities happen just naturally with that element. It's like its decay rate or its disintegrations per second. So if you put a human into the picture, this second one here, this is the number of apples that'll hit the human um, over time. And so that's going to be the absorbed dose. So that's going to be the number of radiation. Say that these are the actual radiation byproducts coming off and hitting the alpha particles or gamma or whatever. These are going to be hitting the person there. So as these particles fall down and hit, that's going to be the absorbed dose, and that's going to be measured in this unit gray. And then the actual effect on the body, in this case, the apple is making a bump on the guy's head, but it could be any kind of other type of effect, the negative effect, negative health effect that will be on the human body. That's going to be the effective dose, and that's measured in the sievert. There's also other. That's the American system, and then the metric system is what I just said, is the Curies and Grays and Sieverts, while in the standard system, we're going to have the Röntgen, RADs, and REMS for activity, exposure, absorbed dose, and dose equivalent. So let's talk about these a little bit. The activity, again, remember that's like with the apple with the trees, the tree with the apples. And that's just its normal activity. It's just normally falling, apples are just falling off of it. As far as exposure goes, that's the quantity absorbed per unit. It's kind of a mixture between exposure and absorbed dose for the second one here. The number of apples that hit the sleeper, that's the gray. So we talk about that as absorbed dose. That's the amount of radiation energy absorbed per unit mass of an organ. So I have these two circled here. This is like the exposure assessment. You remember we talked about risk assessment last quarter. Exposure assessment part would be these two things. It doesn't quite get to the actual health effect yet. So you're not getting to the point where you're looking at what is happening to the body or the organ or tissue. You're just looking at how much of it actually got there. So this is like exposure assessment. How much of it traveled through environment and actually landed to the target organ or target tissue or whatever else. The dose equivalent is then that part. It's the dose response. So that's what is the biological effectiveness of that particular radioactive element, and what happened to the tissue, the target tissue, the ionization that occurred. Here's another figure that I found helpful. So you have the activity of the radioactive source, and that's measured in curies or becquerels. So that, again, is like this one here, with the trees just naturally shedding its apples, and that's this here. You can measure a radioactive source that way. Then you have the intensity of the gamma source in Röntgens. So that would again be quantity used to indicate the amount of ionization in air produced by an X-ray or gamma ray radiation. So that's how strong it's coming off of that apple tree. And then you also have here the absorbed dose, which is how much of it landed into the human body and then converted into dose equivalent that made the physiological effect, and that's going to be the REMs or Sieverts. And again, that's the dose equivalent down here. So that's when the actual negative effect happens to the target organ or tissue. So there's the same factors that happen with exposure assessment and microbes or exposure assessment and chemicals also occur with radiation. So the total amount of time exposed to the radiation source, the distance from it, and the strength of that radioactive source, so the degree of radioactivity. There's a lot of acute health effects that come from ionizing radiation, as well as stochastic effects like carcinogenesis. So let's go back to some of the acute health effects. So at high levels, radiation is capable of producing fatal injuries. At low levels, the dose may not produce something that's immediately detectable, but you can get radiation that will do certain things like nausea, weakness, loss of hair. So health risks of radiation, there's somatic effects, so that occurs in the exposed person. Genetic effects occur to the progeny of those exposed. Radiation effects depend on the rate of absorption, area exposed, and radiosensitivity of cells. So those are a couple of different types of health risks. Again, stochastic effects means that there is an increased probability of the occurrence of an adverse health effect. But that's with time. A long amount of time is usually necessary to a low dose of a lot of things to cause a carcinogenic result. So that's what we say, well, why we use the term stochastic effects. So natural sources of exposure. Well, let's go back to health risks and acute health effects of ionizing radiation. So here on Loma Linda University campus, we use these types of UV lights. I have this one here um, in the lab. This is it's called Purity Products, and it's actually a light. It's just battery powered, but you can use this to essentially um, uh, radiate the surfaces to kill germs. Now, it's like a tanning bed, or it's like UVC, so that's 254 nanometers it's emitting. So you have that type of radiation, and that is actually a type of ionizing radiation. So what happened here on Loma Linda campus is that some people that worked in campus engineering went over to one of the buildings that uses this type of radioactive source for cleaning and disinfecting the air. And so what happened was that they figured that they didn't need eye protection or any protection of their skin, so they walked in there and thought they'd only be in for a few seconds, but they ended up spending about 3 minutes in there. So that was bad news. Okay, here it is. I just turned it on. So I'm now irradiating this source here. Of course, this radiation is not traveling through the camera to you, so you don't have to worry, but this is what it typically looks like. If I was going to shine that light onto my skin for a short amount of time, it would start forming dimers in my DNA, and it would start actually taking things apart. So this is what happened to these people that worked on the campus engineering team. They went into this room that was radiating the air with UV light and UVC, germicidal 254, and they ended up burning their cornea and burning their skin, and they had to go to the emergency room. So it's very serious. And radiation, even ionizing radiation, exists all over the place. So let's talk about natural sources and natural types of exposure to ionizing radiation. So a lot of people are exposed to radon in their home because radon is a type of byproduct of uranium that comes out of the earth. And there's a lot of geologically active areas around faults and things. You're going to have some of this. So around here in Southern California, there are some zones that have radon. Also, cosmic radiation from space and uranium deposits that, those will cause high amounts of radiation levels in some areas. So more talking next about the anthropogenic sources, or how have humans actually influenced the exposure that we have to radiation. Um, there's decommissioned and abandoned nuclear weapons facilities. There's medical X-rays. Back in the 40s and 50s, the amount of X-ray that we were exposed to was much more than we are now. There's also the radioactive fallout from above-ground nuclear testing, and that fallout basically means those particles that are still floating around. Here's some tables. These are from the book as well, and this shows the amount of radiation in in due to natural sources and man-made sources. And this is the effective doses to adults from certain things. So let's talk about uranium. It's common in the Earth's crust, and it has a disintegrations per second rate, so it's actually decaying. Um, Everybody and everything contains a little bit of uranium. So this is a picture from the Navajo miners on the Navajo Nation land at the Karamagi uranium mine. And these uranium mines are all over the place. They're all over Utah, the Navajo Nation. They're all over Arizona portions of the Navajo Nations and other parts, and New Mexico, Colorado as well. Um, this is a sort of a legacy contamination site. Many Navajo people here, they died from kidney failure, and there's also new research that shows that uraniums is in the babies that they are grandfathers of even. So it's a pretty serious problem. Radon, and That is produced by the decay of radium and uranium, and it's classified as a Class A carcinogen. So that means it's definitely going to cause cancer if you have an amount of it in your house. There's extraterrestrial or things that originate from outer space, cosmic radiation, and then there's some nuclear accidents. So a nuclear explosion, of course, the intention is to do a variety of things, but it's nuclear because it releases ionizing radiation. There's different types of ionizing radiation that comes off of one of these things, but usually it has gamma, alpha, and beta particles coming off of it. The intense light from that can damage your eyesight, similar to how UVC can, and also the heat um, can damage things through fire and destruction. The blast, of course, the kinetic blast, that is going to kill and destroy everything within the blast radius. Um, and then as you get farther away from it, you'll have more of the stochastic effects from even many years down the road from the fallout. Here's a famous thing that happened in 2006. Now this is Alexander Litvenko, and he was a former employee, or he was a former Russian spy, as they say it, but the Russian KGB officer and foe of the Kremlin. He died of radiation poisoning, and what they found was that he was poisoned by not gamma radiation, but poisoned by consuming a very small amount of polonium-210, and which corresponds to about 10 micrograms of polonium-210. So that's the really small amount of it, but because it's not a gamma radiation source, most radiation meters aren't really geared up to show and demonstrate exactly what that is. So alpha and beta detectors are much more expensive, and the spies who poisoned him actually didn't know that the U.S. had that kind of technology to detect it. So they were able to figure out that he was actually poisoned by some green tea that somebody had laced with a small amount of polonium-210. It's pretty scary